So in this unit, we're going to start studying about energy and thermodynamics. And thermodynamics is the study of energy and how it changes. And actually, we're going to study a subset of energy and its changes, and that is going to be called thermochemistry. And this subset refers to chemical reactions and energy changes that involve heat. So that'll be the subset of thermodynamics that we're studying in this unit, chemical reactions and energy changes involving heat. I hope you read the text that I had on the website and thought about some of those thinking questions, because we will talk about those in class. So first thing we're going to do is have some definitions. Okay, first thing we need to do is make some definitions. Thermodynamics, I already said, is the study of energy and its transformations. We're going to add a word to your note sheet, thermochemistry. And thermochemistry is the study of chemical reactions and related energy changes related to those reactions that involve heat. So chemical reactions and the energy changes that happen when those chemical reactions take place that involve heat. So in order to talk about energy, we actually need to define energy. And unlike matter, energy has no mass, and we can't see it or touch it. Oh, I'm writing matter. That's a mistake. We want to define energy. So let's write that down. Energy. And so we can't see it, we can't touch it, but we are going to define it as the capacity to do work or transfer heat. So that is our definition of energy, the capacity to do work, lift something up, push something over, or transfer heat. So we have a new word here now. We've added work, so we need to define work. And you'll start, if you're taking physics or if you've taken physics, you'll start to recognize these definitions because they're the same. We're going to define work as the energy used to cause an object to move against a force. So there is our definition of work, the energy used to cause an object to move against a force. And what else do we have? Oh, heat. So we said energy could be either doing work or transferring heat, so we need to define heat. We'll do that in red because heat is hot, actually. And heat is the energy used to cause the temperature of an object to increase. So let's define that. And we don't define cold because there really is no such thing as cold. There is just the transfer of heat. And we'll talk about that more. So those are our definitions. And so now we said that heat is the energy used to cause the temperature of an object to increase. And heat is just the transfer of energy. So now we're going to talk about how energy can be transferred from one object to another. And we're going to talk about two ways energy can be transferred. So when we talk about how energy can be transferred, we're going to talk about two types of energy. And the first one is going to be called kinetic. This is a K. Okay, kinetic energy. And kinetic means motion. And so this is energy of motion. We can measure energy of motion. Our energy M of motion, well, I should have put a K there. It could be EK for kinetic, equals 1/2 the mass of the object times its velocity squared. So we can measure our kinetic energy. I put EM. It could just as easily be EK. And here we have a picture of someone. Well, I actually have to define the other form of energy. So that's our kinetic energy. And I'm going to talk about this picture over here in a second, but it's not just bicyclists and balls and people that have kinetic energy. In chemistry, we're very interested in the kinetic energy, of atoms and molecules. This is kinetic energy of atoms. I don't really need to write this down. And molecules, because they are moving around, and that is how substances transfer energy from the movement of atoms and molecules. We talked about this a little bit last year. We're going to talk about it a lot more. However, right now I want to talk about the other form of energy, which is called, we'll do it in a different color. potential energy. And potential energy you can think of as energy of position. I don't know if that helps, but it's the energy that is stored in something because of its position. So if I hold a ball up really high, there's my hand, I'm holding the ball. This ball has some energy of position because it's above the ground. So it has energy because if I were to drop it, it would hit the ground with some force, kaboom. So when it's up here and I'm holding it, it has a certain amount of energy because it is a certain distance from the ground. And if I were to drop it, then it would transfer that energy to kinetic energy. That's what's happening in this picture. So let's look at that. Let me erase this. Oh, I can't do that now. Oh well. Let's look at our bicyclist. She is up here on the top of the hill, and she's not pedaling. So she has this is a hill. She has high potential energy because she's up high and gravity pulls things down. She's not moving right now, so she has zero kinetic energy. As she goes down the hill, her potential energy decreases because as she gets closer to the bottom of the hill, there's less for her to fall. She's closer to the ground, to the bottom of the hill. However, as she goes down, her kinetic energy increases, so she's transferring her potential energy to increasing kinetic energy. Energy is conserved. We can't lose energy or gain energy. It's like matter. So when we're talking about people riding bicycles, it's easy to see the person moving. The kinetic energy is the person moving. And the potential energy in this case has to do with gravity. If you're up high, then the gravity can pull you down. When we deal with atoms, it's only slightly different. When we're talking about energy being transferred in chemical equations, the kinetic energy is very similar. The kinetic energy, we're talking about atoms or molecules that are moving. So that they're actually moving all the time. And so so their kinetic energy is energy of motion. The potential energy, when we talk about chemical reactions, doesn't have to do with gravity. Gravity has very little effect on atoms and molecules. But there is potential energy in bonds, in chemical bonds, and it relates to where the electrons are. So we're going to spend a little bit of time in this unit and even more in future units, talking about the potential energy created by where electrons are positioned. We're going to have energy of position, or we're going to end up calling it a force, but that is, actually this should be a proportional sign, that is going to be proportional, I'm going to do it in a different color, to the charges that we're dealing with. So if we have two, and that will be our energy of position, our potential energy in our bond is going to be proportional to the charges, let's say if we're dealing with an ionic compound of the two ions, and then it'll be inversely proportional to the distance between them. So it's directly going to, our energy of position in a bond will be directly proportional to two charges and inversely proportional to the distance between them. And this will work with electrons or with ions. We can see in this diagram down here that, where is my thingy? If we have two of the same charges, that as they separate, as the distance between them becomes greater, then there is less repulsion between them, so that our energy will go down. And that will make sense because I'm going to scribble it over here. I said mathematically before, our energy is inversely proportional to the distance. So as the distance decreases, our energy gets less, our potential energy, and that's what we're talking about. This law here that relates charge to distance to energy is called Coulomb's law. And the opposite's going to happen if we have opposite charges. Say we have an ionic compound, so we have a negative ion and a positive ion. As the separation between them becomes greater, then our potential energy is going to increase. So here they're close together and the potential energy is low. But as it increases, as the distance between them increases, the potential energy increases. And by increase, it becomes less negative. So don't worry if that confused you a little. What we're focused on is that molecules move around, they have kinetic energy, and that kinetic energy is going to be what transfers heat. And molecules or ions also have potential energy. And that potential energy is related to where they are in a compound and how close they are to other atoms. So that's the main takeaway here. And the other takeaway is that energy is conserved. We never lose energy. We learned a law last year called the conservation of matter, but it's really called the conservation of matter and energy.